of that one. And the reactive stage is something that is failure to run, that is the reactive stage. And the proactive stage is the preventive maintenance and predictive maintenance. These are the proactive stages. So these are there, and the preventive, these are regularly scheduled one, historical data are collected, and predictive data based on the asset condition and monitoring and analyzing are the basic requirement for the predictive maintenance. Here, the reliability means the ability to perform a specific function and may be given as design reliability or operational reliability. Because this reliability, availability, maintainability, and safety, this is called as RAMS. So I talked to you about this reliability, and that is Vishwasyata. നമ്മൾ മലയാളത്തിൽ പറയാറില്ലേ വിശ്വാസമല്ലേ എല്ലാം. Okay. And availability, that is ലഭ്യത. Availability means ability to keep functioning state in the given environment, that is the availability. And maintainability is the ability to be timely and easily maintained. Now this has come up in the design stage itself, that is what I had understood. And safety means ability not to harm people, environment, or any assets during its life cycle. So today we have with us Mr. Kevin Cherian. Before that, we have Mr. Nitish Devaraj is also here. First thing, Mr. Nitish Devaraj will inaugurate the session. So I will talk about Mr. Nitish Devaraj also. Nitish Devaraj is a mechanical engineering graduate from Marathanesius College of Engineering, Kodamangalam. After that, he started career as a graduate apprentice trainee at Cochin Port Trust, Ernakulam. After completion of training, worked as engineer on contract basis at Cochin Port Trust for 5 years. Joined the Department of Factories and Boilers during 2006 as Inspector of Factories and Boilers. And now he is the Senior Inspector of Factories and Boilers, and he has over 15 years of experience in the field. So I welcome Nitish Devaraj, and also I welcome Shri Kevin Cherian. Kevin Cherian, after doing his BTech degree in Safety and Fire Engineering from Cochin University of Science and Technology, he joined, I think, Western India Shipyard Limited at Goa, and then he moved to Technip India and SR India, and then he continued his MTech studies at the University of Petroleum and Energy Studies. After that he joined Kuwait National Petroleum Company, then Qatar Gas, that is RAS Gas Qatar, and Chiyoda Corporation in Japan. And currently he is working at Chiyoda Corporation, Japan. So we are blessed to have such an eminent personality to talk on the subject matter. And Sri Kevin Cherian is a safety, risk and reliability engineer with more than 17 years of experience in the oil and gas industry and 12 plus in the field of risk and reliability. He has worked in several industries. So first I invite Sri Nitish Devaraj to inaugurate the session, followed by Shri Kevin Cherian to address on the subject. Welcome, Shri Nitish Devaraj.
Thank you, Ramesh ji. Good evening, all. Today is the first monthly evening talk hosted by the reconstituted HSE Forum Committee members. As we know that the members of the reconstituted HSE Forum are people with lot of work experience in the field of health and safety. They are working in different types of industries. This forum also has members with the master degrees in the field of health, safety and environment. I hope they can bring this forum to a national level in future. Different topics need to be discussed in order to make this forum always active. For example, in all factories, there are near misses and non-reportable accidents. Every near miss and non-reportable accidents are different in one or other way. The factory management investigate about these in detail and take preventive measures. Corporate organizations have their mechanism in place to communicate these incidents and preventive measures to their institutions of their own. But we do not have a mechanism to make such information available to other small and medium factories. Therefore, if all these are discussed in this forum, in monthly talk or otherwise, it is possible to prevent such accidents in other factories. It may also save someone's life. The subject we are discussing here today is also a unique one. It is Introduction to Reliability, Availability, Maintainability, and Safety Studies taken by Mr. Kevin Cherian, Reliability Consultant. I hope that those who know about this subject will be able to refresh their knowledge, and those who do not know will be able to learn basics about this subject. I formally inaugurate this evening talk session. Thank you.
Thank you very much, Nitish sir. I think we will take your inputs very seriously regarding taking up the near misses and non-reportable accidents. Also sharing in this for some way the HSE forum would try to have some information sharing and learnings from each other and make our place much better place to work with. Now I request Mr. Kevin Cherian to proceed with his evening talk. Over to you, Mr. Kevin.
Yeah, Mr. Ramesh, thank you. Thank you for the introduction. Respected guests, members of the National Safety Council, and my dear friends. Welcome to this introduction on reliability, availability, maintainability, and safety studies. As you can see in the picture, you can see 4 circles with 4 different functionalities. There's reliability, there's safety, there's availability, and maintainability. Well, before we start, just to get some clear understanding, reliability and safety are basically generally have very 2 different functionalities. Reliability is reliability, maintainability, and availability. All 3 of them together are more of what you consider an asset management process. You're more focused on maintaining your asset, make sure your asset is available. And when you say asset, you're talking about maybe a pump, a compressor, a unit, the entire process plant, anything. So it's basically your asset, like your car, your TV, your mobile. All these things are assets that you have. It's exactly the same case with when you're working in a plant. Safety is more of a risk management process where you're trying to reduce the risk of a potential incident, like your near misses or maybe accidents or hazards or safeties for fatalities or permanent injuries. But there is always an integration in all of these elements to make sure your plant runs safe, your plant runs smooth, your plant is in perfect condition. Nobody likes to have safety incidents, even if it's related to humans or if it's related to factors which have come from equipment failures or process failures in the plant. So we move on. There's a few slides. I'm sorry, I had some trouble with my microphone, so I think we've lost a few time. Yeah, a lot of time. So we move on to the next slide. I don't know who's controlling the slides. Can you hear me?
Meenu, can you put, yeah.
So so reliability, availability, maintainability, safety, normally called as RAMS. Generally, it's termed as a RAM analysis. You don't have the S sometimes, but now it's very specific. People say you need to have safety also, and it makes sense. In Europe, I believe they have specific standards for RAMS analysis for safety also. Not everywhere else. Generally, you don't have specific standards. You do have reference documents like IS 14224, which talks about exchange of maintenance and reliability data. Lots of ISO standards, but I don't believe we have a specific standard, a national standard maybe, or international standard that really covers it. I believe there was something with the OISD petroleum natural gas guidelines, the rules, which mentions something about RAMS analysis, but it's not very specific. Anyway, we go down to the topics. So what we will cover during this presentation is, if you can go through the slide, we talk about what is RAMS, why we do RAMS, what are the various elements of RAMS, who are the stakeholders of RAMS, what are the definitions of each element, reliability, availability, maintainability, dependability of each of these elements, configuration, some basic configurations of how you normally do your RAM analysis, how safety studies can be incorporated into this, and what are the challenges we normally face when we do a RAM analysis. Next slide, please. So what is RAMS? RAMS is a systematic asset management program to ensure optimum safety, reliability, availability, maintainability during the life cycle of the plant. So what you need to understand is RAMS is systematic. When you say systematic, you're basically saying you're breaking the plant into different sections, subsections, components, until you finally go to the last section, or individual components, or your functional locations, or your tag numbers. You normally say tags, like your pump 1, pump 2, all those specific tags that you have. You normally break it down to those components, and then you analyze the reliability, maintainability, availability all together as a system. So that's what you say systematic approach. Asset management, because you say management, it's like I mentioned earlier, it's all about equipment safety, equipment reliability. Optimal safety, you don't compromise on safety. Safety is your highest priority. So there's always a factor of safety that is involved in every analysis. In every process in the company, you'll always say safety is the highest priority. Might not be the case in reality, but it is still the highest priority, because there are lots of obligations that you have, legal obligations, moral obligations, financial obligations, whatever it is. Safety will always be our highest priority, and it's always good to be a safety professional working in reliability. So reliability, availability, maintainability during the life cycle. So if you look into the definition, life cycle, you normally talk about the entire life cycle of the plant. So it's normally about if your plant is running for 30 years, that's the life cycle. It's an open live program, so you're continuously doing a process where you're continuously updating your RAMS analysis. It can start right from your design stage. You can go into your conceptual stage, your feed stage, your detail engineering stage. You can do it at every cycle of the plant life. So it's a live thing, and you have a management process to basically follow it up. It's normally measured as percentage availability. So it comes down to just one single figure. If you want to know your plant is available or not, it's It's defined as percentage of availability. And percentage availability is normally not reflected. It's reflected as profitability in the end. So basically, it's what's interesting to your plant owners or your management, know that your plant is available so that they make enough profit as long as it's safe. We go to the next slide. Yeah, so that's what it is. Basically, reliability is basically talks about RAM analysis. Basically, talks about how much returns you get on your investment. But if you can see the picture, you can see a person, a Hollywood celebrity. I don't know if you know him, and you can see him screaming out, "Show me the money." Yeah, so it's a very famous dialogue that from a movie, and I thought I'd just like to maybe correlate it to this incident. So this is what it is. It's basically it's all about money as long as you run the plant safe. So safety in RAMS is always the highest priority because management always likes to reduce the cost, reduce your expenses. So it's important you put safety in the picture, or you could have a lot of failures and disasters and safety incidents. So we go to the next slide. So who would be interested in RAMS? Your investors. If people invest in your company, say you have a company, you have an investor, maybe your plant owners, the people who run the company, your DCO, your CEOs, your MDs, all the people in top management. They need to make sure that the assets are functioning properly. These are basically KPIs for them. If you don't maintain your KPIs, it's a big problem for them too. So they need to make sure it's available. Your asset management team. So if you're in operations, you basically have an entire team pertaining to a specific asset. You have your chemical engineers, your electrical engineers, your instrument engineers, your mechanical engineers, your rotating engineers, your static engineers, your reliability engineers, your safety engineers. You normally form a team for every specific area. So if any specific area in the plant is not really functioning well, you know who's accountable, who's responsible. So they would have to make sure that the plant is available. So your asset management team is mainly someone who's in operations and who's responsible for the functioning of those assets. Now you have your project management team. This comes when it comes to when you're doing new projects, not when you're in operations. If you're a consultant who's in charge of ensuring that the design you make is reliable, you will also have to be accountable to this, because they would in turn distribute the load to the EPC companies, or your engineering companies who really do the engineering designs, and they in turn, if you can see the engineering team, the EPC, design engineers, loss prevention and safety engineers who are all working in the engineering side, they would also have to focus on maintaining the availability targets. If you look at it really, RAM analysis is technically mostly done during the engineering phase. There's a reason, is because management always wants to make sure, or your investors want to make sure that the design you make is really what you say it does. You might say that your plan is, your design is really good. You've done it. You're very reliable and all, but in the end, you need to really prove it to your investors or to the clients that your design is really available to attain your desired target. So in the end, the client side or the investors basically set a target. We say, if I want to get my return on investment, I need to make sure my plant is running at 98% capability. So you obviously have maybe a 2% failure in production, and I will just push it away. I don't mind, because if I can guarantee a 98% availability of my plant, then that's good enough to get my returns. So who else is interested? Logistics, they can be affected. End users, your customers. If your plant is not available, your customers are not happy. They don't pay you. If you don't get paid, you don't pay your employees. Nobody's happy. So customers and students, or anybody who's trying to pursue RAM analysis in the future prospects, they would also be affected, or interested. So we can move to the next slide. So we are. If you look into the definition of RAMS, I earlier mentioned that the plant is basically split into different systems, subsystems, components. So this is a general definition. All process plants in general may be considered to be a complex arrangement of equipment, which can be broken down in series and parallel, and combination of both these series and parallel of both to process raw feed to get your product. So it's just an analysis of breaking your plant from a complex structure to a very simple process structure. So that's the whole idea of RAMS. It's mostly done during your engineering phase, because it's engineering teams that normally has all your design data right from the beginning. If people do it even during the manufacturing stage, when you have vendors do it in their plant facilities, but it's very specific to the equipment. When it comes to the engineering phase, you need to treat it as a whole system. So that's RAMS, the system, subsystem, and components. We can go to the next slide. This is a typical layout of an LNG facility. I don't know if it's visible. I'm looking through my phone. So if you look at on the left side, you can see feed that comes from your upstream facilities. It goes down, goes to your sludge.
ഇതിന്റെ പൊസിഷനാണ് ഇതിന്റെ പൊസിഷൻ മാറ്റിയപ്പോൾ വീണ്ടും പ്രശ്നമായി. കേട്ടോ, ഇതിന്റെ എന്താ വയർ ഡിസ്കണക്ട് ആയി.
I think please mute.
We are good.
Go ahead, Kevin.
Can I proceed?
Please proceed.
So this is a typical layout of an LNG facility, where you get raw gas from your fields, your offshore fields. It comes and gets processed, and you finally get LNG and shipped off to from your terminals to companies like Petronet or any other companies that basically handle LNG. So it's some basic units and subsystems and equipments. They're all compiled together in this. So you can see right from the beginning, you have the feed that's coming in, goes to the slug catcher, gets separated. The gas gets separated from the liquid and from the condensate. And you can see the gas is what we are interested in. So that's coming from the top of the slug catcher. It goes to an HP separator. You again separate your gases, bring down the pressure. It goes to your AGR unit, your acid gas removal unit. You remove the H2S. It goes to your CO2 removal system. It brings down the ppm to 5 ppm, or less, right? I think it's 10 ppm. I'm not sure. I can't see it from here. Then it goes to your dehydration and mercaptan removal unit, and then it goes so on, so on, so on, till you finally get your product. So this is a typical layout of an LNG facility. Now we will see how this system can be broken down into different units, subunits. equipment so that we can perform our RAM analysis. Yeah, we can go to the next. Yeah, so you can see the feed gas that we saw coming to the slug catcher. That's the first block. So these are basically your systems. You can see the battery limit, something aligned with the stripes. That's your battery limit. So that's the boundary. You decide as a company that the upstream facility is not part of your plant. You're not going to include it in your RAM analysis. Everything under the inside the battery limit, yeah, we include that. Even if your feed gas quality or production rates might vary. So yeah, it comes in. And these, what you see next, are basically the different levels of systems. So you have the top level, which is your LNG plant itself. Yeah, your LNG plant distributes the feed to 3 different trains. So you might have one single feed line, or you might have 3, depending on your configuration. You might your 3 separate trains or 3 separate strings. You normally call it trains or strings. Most preferably, they will be identical in design. The entire string would be more or less the same, as long as the feed rates and the production rates are the same. If you can look through the closer, you can even see the production rates are mentioned in the block diagram. So you can see 500 mmSCF. That's a gas feed rate coming to each train. So for mmSCF is basically the unit that you measure gas. It stands for standard cubic feet. Mm stands for metric or million, depending on how you want to read it. So yeah, each train has a separate set of units in the next layer. So you have unit 1, your inlet facilities, unit 2, your AGR, unit 3, your dehydration mercaptan removal, and so. So that's your next unit, next level of units. And then if you go to the last, you have your individual components, your pumps, your compressors, your exchangers, your turbines, and all those equipments. So what you do in RAM analysis is you normally equate or calculate each and every single reliability and availability of each and every single component in the system. And then you add it up or combine it. And then you go to a unit level, and then you combine that. And then you go to the higher hierarchies and hierarchies. So if you want to know what hierarchy needs to be in place, you can always refer your IS 14224 standard, which talks about the exchange of maintenance and reliability data. So this is basically just a layout of how you should basically split your plant or your systems so that you can go into each one of them individually and basically calculate your availability and your reliability, maintainability, and availability data. Right? So you can go to the next slide. Yeah, so this is what we're really looking forward to. This is what you finally end up with. It's called reliability block diagrams. So if you've worked in an EPC or in operations or in design or with a consultant, you probably might have seen this. It normally tells out about how your load distributions, how your feed, how your equipment redundancy is laid out. RAM analysis is all about equipment redundancy. The objective of RAM analysis is always to attain maximum availability at minimum cost, minimum maintenance cost, minimum operational cost. But yeah, you don't bring down your safety cost because you cannot compromise on safety. But yeah, so when you do your analysis, or when your engineering company does it for you, they say, yeah, we have done a RAM analysis on our engineering design, and they say management, or to the client, they say, yeah, it's a bit low on availability. Yeah, you told us to get a target availability of 98%, but our design is only can only give you 94%. So your maintenance, so your project team, your process technology team, your process engineers, everybody sits together, sees how you can reconfigure your plan, and they decide, yeah, maybe we will include another equipment in the system, and we will increase the availability. Now, we will go down into that a little more in detail later. But if you look at these equipments, yeah, you can see the feed gas coming in at 100%. As you go, it goes to the surge drum, as we saw earlier. Then from the surge drum, it goes to a metering skid, where you meter your feed gas, and you basically you consist of analyzers, maybe filters. Your analyzers give you what's the feed quality and all those stuff. If your analyzers fail, you really don't know what's the quality of the gas that's coming in. So you might have contractual agreements with the upstream company saying that you need to give us material at this quality. Our systems can only process that much of gas. You cannot have. Sometimes you have condensate coming in a lot of condensate. I remember we used to have in one of the companies, they were sending condensate to the gas lines because the condensate lines were basically in a failed state. So they were just sending all the feed through the gas line, and there was a lot of hydrate formation, and because yeah, basically your trains were not designed to handle so much of liquid in your gas lines. So yeah, a lot of arguments, a lot of heated discussions. So it's always, you have these gas skids, and it's always important that they have some redundancy factor. So if you look into what's going into the system, you can see there's a load distribution. So 100% of your feed goes into your surge drum, and then once it enters your surge drum, it then further goes to each of your metering skids. But it's not 100% that's going to each skid. Yeah, you get a 50% of the load that's going into your different skids. So if you have 100% of your surge drum, 50%, 50%, and 50%, that's three different metering skids. So they are basically designed to handle 150% of the feed. So what does that mean? It means if one of your metering skids, if one of your analyzers fail, yeah, it's all right. It doesn't really make a difference because the remaining two analyzers can basically handle 100% of our feed. And now what happens if you lose two of your metering skids? Yeah, now you have a problem. You can still run the plant, but you need to maybe run it at a lower capacity. So now you need to run your plant at a 50% capacity. If you lose all three of your skids, yeah, you need to go to a total plant shutdown. So this is the concept. Do you want to run at 50%? Do you want to run at 100%? You might have to do a combination of calculations to see what is your final availability. It's a bit complex in the system, so you always have all these softwares to help you design to calculate your final availability rates, especially when your system is very complex. You have companies like D&V, Vectra, and all these companies who are specialized in RAM analysis for the last 40 years. They're normally the go-to consultants who do RAM analysis. But this is the concept. You can even derate your equipment. You see, it mentions 50% for each of these metering skids. Sometimes if it fails, you can, operations says, yeah, maybe we can run it at 70% capacity because yeah, we have too much demand from your clients or from your customers. Yeah, we have to provide the customers. So yeah, it's something that you call derating. You run your equipment on a higher load than what it is designed sometimes. So yeah, these are different options management thinks about when you do a RAM analysis. At the end of the day, you really need to make your customers happy. I used to remember in one of the companies, we were working in a refinery. The refinery's processing capacity was 180,000 barrels. Yeah, for some reason, one of the columns, the CDU columns, was almost non-functional. So they were running the column at 220,000 barrel capacity rate. What was happening was they estimated that the equipment itself was okay. Yeah, it was okay, but all the process downstream of the equipment really couldn't handle the load. Yeah, it's designed for 180,000. Every equipment down the system is only designed for 180,000 barrels. So yeah, your desalters on the top, or your naturalizers or stabilizers, all were functioned designed to only handle that much capacity. So what was happening was, yeah, your desalters were not functioning. Top pump around was causing too much corrosion in your system. The top of the column basically went for a total degradation failure and basically just ruptured. Okay, so these are things you need to understand. Your reliability block diagram is the most important component of your RAM analysis. It helps you finally do your final calculations when you to get your final reliability, availability, and maintainability data. Right? Okay, we go to the next slide. Yeah, so I also mentioned that RAM analysis is a systematic asset management process. So yeah, when you say asset management process, when you talk about management process, it's all about a continuous improvement cycle. You find that everywhere in your ISO 9000s, your 14,000, 18,000, 45,000. It's all there, the PDCA cycle. We call it Deming cycle, I think. Deming was considered a forefather of quality. It's kind of a quality approach. So these are basically, this is the management process, basically just indicates a process that's in loop following the PDCA cycle, the plan, do, act, plan, do, check, and act cycle. What I mentioned down, you can also see the same cycle is followed during every stage. Yeah, you do a RAM analysis during the conceptual stage. You might get some inputs later. It's not possible to do the entire RAM analysis in the conceptual stage. Conceptual stage is this, you have an idea. You really don't have all the data, the equipment list. You don't have all the processes. You've not finalized on everything. So you can do a RAM analysis, but it wouldn't be complete. So then you would have to go to the next stage, which is your pre-feed stage. You will do this again and again and again till the plant life, till the end of the plant life. And you will ensure that your availability will either meet the deadline, or you might even have KPIs to improve. If you already have meeting the targets, you can always increase your availability targets. Yeah, you might have had a 94% in the beginning. Yeah, you got a 96%. Later you see, yeah, 96 is a piece of cake. We go for 98 and 99 and maybe 99.9. So it's all about revising your targets, revising your designs until, yeah, because money is money. Right, next slide, please. RAMS at various stages of the plant life cycle. As we told right in the beginning of the presentation, before my presentation, Sir was talking about RAM analysis being done during the engineering phase, and he was exactly correct, because yes, it is done mostly at the engineering stage, but you also do it other stages. These are the different stages and what kind of RAMs you do at each stage. So your conceptual stage, you're just comparing various basic designs. So you really don't have much of options. You're looking at all the ways to run your plant. You might have a compressor You need a lot of, you need a driver for the compressor. You want to decide which kind of driver do we use. We have a lot of steam being generated in one of our boiler units. Yeah, we can use steam. We don't need steam. Using a steam turbine would probably be the most optimum option for us. You say maybe we run our own power grid. We can go for an electrical motor instead of a steam turbine. So you look at and sorry, somebody wants to say something. Yeah. So these are the different cycles. You can in the feed stage. You have already identified critical components affecting. Yeah. The idea is to identify critical components. Yeah. So during the feed stage, you have more of data. So you have more of equipment. You have more of your basic design is almost configured. You're trying to calculate the RAM or your availability data for all those equipments that you have at hand. And then it goes on from each stage. You go to the detailed engineering. Now you kind of have your design, which is fixed. You're almost going to make no changes. It's just the detailed packages that you need to work on. So you are mostly working on getting vendor data. Your vendor provides all reliability data, your maintenance data. It gives you all kinds of data, your equipment data. If you look into your pump data sheet, you'll see the pump is designed to run for 80,000 hours, 100,000 hours. Your bearings have life for 40,000 hours. Your seal has a life of, so it all gives you an idea when you can expect your failure. So it can give you more data to calculate your availability, reliability, maintainability, and availability data. We can go to the next slide. Yeah, so now we talk about the dependability of safety, reliability, maintainability, and availability. On the left, you can see all those various safety studies that you follow in your companies. You do PHA, your process hazard analysis, your hazard and operability studies, your QRA, quantitative risk assessment, your EIA, environmental impact assessment, your SIL studies, your SC, your safety critical elements, and ERM, enterprise risk management. And on the right, you can see studies more related to reliability, maintainability, and availability. So you do a criticality analysis. That's kind of a responsibility of the reliability team. If you work in operations, you know that every equipment is designated a criticality, and based on your criticality, you will always make sure your plant equipments are functioning either through design or through maintenance or through operations. So it is probably one of the first steps you do once you get your entire equipment database is to assign a criticality to your equipment. Root cause analysis, normally done when you have a plant failure, if your plant trips, and it costs a lot of production loss, and you lose millions of dollars. Then you decide you will do a root cause analysis, and you will do a risk assessment of the incident, and then you will do a detailed analysis with the team. It's normally facilitated by the reliability engineer, sometimes even by the safety engineer. If it's a safety critical incident, if it's caused maybe some fatalities or some environmental damage. Yeah, so there are links. Now your SC, your safety critical element, is basically a safety study. In most companies, especially if you're in operations in the Middle East or in Europe, it's a very common thing to do a safety critical element analysis and develop performance standards for that. So if you look at it might be termed as different safety critical elements in safety, criticality analysis, in reliability, but in general, they're both functioning the same function. So, but nonetheless, many companies still do separate analysis. They don't really merge all this together. It doesn't make any, it doesn't help anybody to redo the work. So it's always one of those things that you can think about integrating together. And this is where reliability and safety and can come together. I remember in the last company, as a reliability engineer, I was responsible for doing the safety critical elements, while in the same in different organizations within the same country, it was a responsibility of the safety engineer, or at least they were the program coordinators for it. Because in the end, it doesn't make any difference. It all ends up in making sure your plant runs safely. So other analysis, you have a reliability analytics. This is again to make show management what are the factors that have affected your production loss, your extension and turnarounds, all those factors. It's normally used to as a presentation to get all the data to present to your top management. Yeah, so it's normally one of the other studies that reliability does. Bad actors are common in both safety and reliability. Reliability focuses more on equipments, safety more on human safety, and what are the factors, the bad actors, which are contributing to your near-miss incidents, or safety incidents, or failures, or lost time incidents. FME, RCM, RBI, these are normally maintenance related maintenance studies, as mentioned earlier, about reactive and proactive maintenance. This is exactly the same. You use FMEA studies or RCM studies or RBA studies to basically determine, use a risk-based approach to basically determine what are the maintenance strategies or the maintenance tasks that needs to be done. Now, when you say a risk-based approach, you're basically using a risk matrix where you will have factors affecting safety, you will have factors affecting environment, your health, fire, you have factors affecting your production and your probability. So in the end, most of these studies, they all function on the same principle of doing a risk assessment study. You do quantitative risk assessments. Yeah, you're doing more or less the same process. You do your hazard identification. You see how these hazards can fail. You see what are the risks associated to this. What are the consequences? What are the probabilities? So everything in the end, it all follows one cycle where you're doing mostly a lot of risk assessment on what are the possible things that can go wrong. This is where reliability, availability, maintainability, and safety can be integrated together. Many times what happens is different companies, the company can have, can be doing all these studies together, but they would never be linked. So if I have a risk that has already been calculated in your quantitative risk assessment, the best thing what I would do, and if I wanted to use the same risk, or if I wanted to do a risk assessment on the same equipment in another study, so I have a tower or a vessel, and QRA normally does its own quantitative risk assessment study. At the same time, you have maintenance department, or reliability department, which does another study on the same equipment. Now, all you need to do is basically use the same risk assessment, and you form the same team, but it never happens for some reason or the other. These are all normally kept very separate, and the work is just redone and redone. So it's just doing repetitive work without productivity. I believe with your integrated management system is one of those approaches where you integrated the ISO 9000, the ISO 14000, OSHA's 18000. So yeah, that's kind of integration. This is what you need to do also over here, and this is where we need to see where safety and reliability can work together. So this is basically dependability, where you can normally use a lot of data from one study into the other study. Personally, I believe quantitative risk assessment can do a lot more in reliability, if you do your risk assessments properly using your quantitative risk assessments. But normally the objective of a quantitative risk assessment is very much different. So it's always kept separately. We can go to the next slide. Yeah, so this is a typical risk matrix that you see. It's really not visible from here. So anyway, you have probability and on one side of the chart, and you have your consequence on the other side. So your consequence can be on financial aspect, from the safety aspect, from your environmental aspect. Yeah, so now again, different, like I mentioned earlier, different studies use different aspects of the consequence chart. So your asset management tools primarily focus on your production financial consequences. So you can see there's low financial consequence if it's $10,000. Yeah, maybe it goes medium if it's 100,000, and it's very high if it's 1 million. So yeah, but even if your equipment has a low financial consequence, and if it has a high safety consequence, your equipment can still be assigned a high criticality. So that's the thing about doing any risk assessment. If you're going to include all these factors in reliability, yes, you do include safety as one of the factors that affect consequence. So if your equipment is critical and safety critical, and if it's not production critical, the criticality will still be high for your equipment. And now in general, if you go to a plant, your equipments, like I mentioned earlier, are all assigned criticality. There's a standard thumbs up rule that says about 20% of your equipments are all safety critical, 30% are business critical, or another 30% is maybe just business critical, but not with any financial consequence. And you can have another 30% with just run to failure. So you basically don't need to do any maintenance tasks. Rather, you just replace it on demand or on failure. So the problem with all these studies is sometimes you use different risk matrices. I was working in a company where they used 12 different risk matrices. We had a consultant come and he said, yeah, we asked them whether we could integrate this. And they said this is literally impossible. You use 12 different risk matrices. The criticality for each of your equipments, for each of your studies are different. So it becomes a big problem in the end. We really don't know how we can integrate this all together, because in the end, we want to assign tasks based on to reduce your risk. And if an equipment shows it's a high safety risk in one study, and in another study it says it's not really posing any threat, there's no real way to integrate it, because there can be a lot of conflict of interest.
This is the one we need to write. See, RH or any else liner. I'm going to wait using power.
Right. You want to ask something? Oh, we go. Okay. You can go to the next slide. Yeah. So what are the normal data that you require for RAM analysis? So you have the master data list. So normally engineering companies give you an entire master data list with all the equipments in your list. It includes your safety equipments, your business equipments, your production equipments, your all the equipments. It gives you entire list. It tells you what the functionality of this is, what are the operating limits of this. All these factors are normally listed. You have your PFDs, process flow diagrams. It helps you build your reliability block diagrams we saw earlier, all the configurations. Your P&IDs, process and instrument diagrams, your cause and effects. You see how things affect each other. Your design philosophies. Your design philosophy is what your process technology team gives it to you. You need to know what happens if equipments fail and how much of derating will be going into the system, how you can do the load sharing and all those factors. So your design, operability philosophy, your maintenance strategies, your maintenance, like I said earlier, your maintenance, your vendor data can give you a lot of information on your mean time to failure or your equipment failures, and you can use it for the analysis. reliability failure data. Yeah, reliability failure data. Yeah. Equipment manufacturing vendor reliability data. So all this equipment reliability failure data, what I was meaning was basically in operations, you normally have live data. The data that you have is actual data. So you call that actual reliability data or failure data. Is normally taken for your maintenance systems. It's not always reliable, but you need to do a lot of verification on it. So all this data is something that you can use as an input for your RAMS. It's actually the most important thing for your RAMS, because you need to always see how you can change the way you can do your repairs, change the way you need to order your spares, change the way you need to increase your reliability. You might have to change your equipment to increase the reliability. If the cost benefit analysis says, yeah, it's better to change your equipment if it's not reliable or if it's not safe, it's always better to, so you can do all those analysis when you have real data. If you don't have real-time data, you need to assume a lot. That's what the consultants or engineering companies do, is there's a lot of assumption into your data, especially when it comes to probability of failure or your consequence, which is why it's very important you do all this analysis as a team, where you have operations present, where you discipline engineers. So if you're doing a RAM analysis for your pumps, you need to make sure that your maintenance engineer or your rotating equipment engineer is with you, operations is with you. They can tell you the actual data, or you can even take it from your process trends or your process engineer and all those things. So yeah, you have equipment manufacture data, you have your hazard sales studies, your safety critical elements. Another great area, your maintenance history, reliability analytics, kind of extrapolated data, process trends. All these things can be used, your national and international standards. You have a lot of data that is available and which is readily available. Your offshore reliability data or your offshore and onshore reliability data, it's called ORIDA. ORIDA is what most people use. I prefer using ORIDA. It normally has data on failure rates, your repair rates, how long does it normally take, to, what are the normal failure modes. It gives you at least something to work on, though most companies nowadays prefer using their own data. I was speaking to a person from an offshore company, and he was saying, yeah, we don't use consultant data, or we don't use ORIDA data, rather we use our own data, our own failure rates, because it gives us a more clear idea of how our equipments are failing, rather than compilation of data that comes from somewhere else. All right. So these are just the basic data that you require for RAM analysis. It helps you, makes your process easier. We go to the next slide. So what is reliability? Reliability is the probability that an equipment performs a required function under stated conditions for a stated period of time. So you have 4 factors in what makes what defines your reliability. You have the probability. You normally say your plant is your equipment is 90% or 99. 99%. That's a probabilistic figure. That when you say your pump is 90% reliable, that means it's a 10% unreliable. So we are more interested in the percentage or the failure rate or the MTTF, because that is what we need to work on. We need to improve on the reliability. The probability needs to really go up. So probability, like I said, it's basically a target or a goal. 99% reliability for your fire pump. Yeah, good. The required function is to pump lube oil to the moving parts of the compressor. Yeah, so as any pump, that's the required function. You can't use your pump to do some other function and say it's not reliable. So you can only do what you asked your engineer to design it for. Then it performs. As long as it performs the required function, yeah, you get this much percentage reliability. Stated conditions, yeah, your temperature conditions, your pressure conditions. Yeah, so your pump should pump liquid at a specific, if your pump pumps it at a specific design pressure, 1 to 10 bar, or a specific design temperature, 40 degrees Celsius, then your pump we give you a guarantee that your pump will fail after 80,000 hours or 100,000 hours. So that's the guarantee the vendor gives you most of the time. We in operations, you kind of push your equipments to the limits. It's not really their fault. If you're working in the Middle East, your equipments can go up to 50, 55 degrees Celsius. So yeah, there's a lot of boundary conditions that prevent your pump or your compressors from functioning efficiently. So that's your stated condition, the stated period of time. Yeah, so that's your life, which normally you say your pump is reliable for the next 10 years, which is also comes with your vendor data sheets or manufacturing OEM data sheets. So this is four factors that go on reliability. Probably the equipment will function for the required function under stated conditions, stated period of time. This gives you reliability. This is your first and most important step of the RAM analysis. Is you need to calculate the reliability for each and every component of your plant, right? And then you go to the next step. So we go to the next slide. So this is reliability. This is the basic formula of reliability, which is considered the formula during the useful life of the plant. So you can see the curve. It's called a bathtub curve, or you can say it's a Weibull curve. It's basically a distribution of your failures, and says, yeah, you can see in the early stage it says something like infant failure, or it's something that happens during the early stage of your plant life. Then you have something during the mid stage, and then you have something during the final stage of your plant. The normal calculation, what you see over here, the R of T is equal to E raised to minus T by MTBF, where MTBF stands for mean time between failure. We will go into that later. So this is the basic formula, but it is only used during the useful life. So if your plant starts is commissioned in 2000, the first few years from 2000 to 2003, you can expect a lot of failures, and that's all right, because it normally happens when you commission a plant. Normally your engineering company gives you a performance guarantee. It says, yeah, we will make sure we will operate your plant for at least 1 year, and then we will have. So there's anything wrong with your plant, yeah, you have nothing to worry. We will cover the expenses. That's your performance guarantee. They give you performance guarantees for even more, 10 years continuous life cycle throughout the entire life cycle. They give you continuous support as long as you pay them. So this is the formula. But if you're going to, which is pretty much easy, but if you want to know the reliability for the entire life cycle, you cannot use this formula. You need to use another formula, which is more calculated based on your distribution rather than the failure at a certain point. So, but these are normally done during by software, so you really don't have to worry about it. So MTBF stands for mean time between failure. It's also called MTTF or MTBF, mean time to failure or mean time between failure. These are things you normally see in RAM analysis or reliability analysis. And so yeah, you can see a bit of calculation. It's the same thing. You have a T, you're expecting the plant to run for 1 year. Yeah, like I said, it's not the entire duration. You're just looking at a year. So somewhere down half-life of the plant, you're calculating using this formula. It's fine. And your MTBF is, yeah, you say it's 800 years. Then this is the formula you use. So in short, reliability is quality over time. So quality basically takes care of defects during design. It makes sure that your plant is good in the beginning, but how you run it at the end, if it fails, yeah, it's all about reliability. It's not quality. Now companies do a lot of research.
Mr. Kevin.
Yes, sir.
Mr. Kevin, sorry to interrupt you. This
Yeah.
mean time between failure, you mentioned 800 years. Usually for any equipment, machineries, it has a
validity, for as per OEM, maximum 100 years. So this 800 is a huge duration. On what basis they decide this is 800 years?
This is just an example.
Because plant
It's
life
just an
itself, limited years.
Yeah, but you're concerned
Yeah,
about
but this figure seems to be very high.
It's just a calculation. It's just a random figure that I put in. It doesn't matter. It doesn't matter. What we're really talking about is only about the calculation. What you were saying again? Can you just repeat it? I didn't really. You're saying your plant life.
Because usually plant life, maximum 100 years, 150 years, then it go for decommissioning stage, and that is the life cycle of any plant. So yeah, because 800 years is very huge for any plant equipment and plant operations. That's why I'm asking.
Well, we can. It's how you design your equipment in the end. But yeah, 800 years is definitely too much, like you said. But it's just a figure. It's just a figure. You don't really need to go. If you're looking specifically into any equipment, yeah, we can go into the details. But yeah, this is just a random figure. It's just a general calculation. It's not even for the equipment. It's just a general calculation that I put on the table. We can when you do.
I got it.
Yeah, so I will give you another example in the next slide. This is just like I said, it's just a basic calculation that we put. Isn't meant to actually mean anything. Just to understand the formula.
Yeah. I understood. Okay, fine. Just a random figure. Yeah.
Okay, so we can go to the next slide. Or you want to discuss this more? Okay, so RAM talks about different equipments in different configurations of equipments. Like I said, I showed you earlier the entire layout of the equipments. You had all the individual reliability block diagrams. So all these calculations, all these figures, or these reliability block diagrams can be expressed in some basic mathematical tools, which we might have all studied at some stage in our life. So we talk about reliability of equipment in series, reliability of equipment in parallel. There's a combination of equipment in series and parallel, and you can have R out of N configurations. So there's you can have multiple different kinds of ways your plans are arranged, and this basically covers each and every stage of each and every type of configuration that you can have in your plan. So we can go to the next slide. Yeah, so these are basically three identical components. I might have written the component number wrong. It's three identical or three different components with the same reliability. You can assume anything you want. Basically, it's component A, component B, and component C. I got the C misplaced. So now how do you calculate the reliability or the availability of this equipment altogether? Is basically you just multiply each and every reliability figure together. So if component A is 0.95% reliability, component B is 0.95, and component C is 0.95. When you sum total, or when you look at the system as a whole, your reliability goes to 0.857. So if you recognized it, the total probability or the total reliability of the figure basically goes down when you have equipment in series, right? So that's something that you need to keep in mind, that the more equipments you add into a system, you're most likely to decrease the reliability of the system. And that's the nature of the system. You're only as strong as your weakest link. So this is something you need to keep in your mind, right? So we go to the next slide. Yeah, now we talk about equipments in parallel. We talk about A, B, and C. The same configuration that was initially in series is now being put in parallel, right? It's again not based on any equipment history or something. It's just something I just randomly put in this just to have an understanding. So when you talk about equipments in parallel, the same equipment, when you put it in parallel, the calculation is a bit different. you can look at the system reliability. It's 1 minus R1 times 1 minus R2 times 1 minus R3, and your final system reliability goes to 0.9998. So you get 99% reliability now for the same equipment that is in parallel than to the ones that were in series. So this is exactly the basis of doing your RAM analysis, is that when you change your configurations, when you include a lot of redundancy into your system, you can basically increase your reliability. So this is the basic concept, and this is what is probably one of the most important concepts, which is something that you keep in mind too. So we move on to the next one. So now we have systems which are in combination. So you have block 1, block 2, block 3. So you have one equipment connected to another equipment. You have one block. Sorry, not one equipment. So I like to think of the block as a unit where you have add more in series, more parallel, depending on how you want it to be. Yeah, you have block 2 where you can have maybe you can consider your pumps or your skids, which are in parallel. And then you have block 3, which is maybe your next unit, where you can have, again, different configurations. So this is basically a combination, and this is how it's normally at. You might have, as you saw initially in the block diagram, you had the surge drum connected to the metering skids. So the metering skids were in parallel, while your surge drum was just one individual equipment. It's not really practical to have too many equipments, but yeah, for some of the equipments, like your rotating components, you can expect a lot of wear and tear. So the equipments can normally fail at a pretty early stage. Like Sir was talking earlier, yeah, the MTBF was too high. Yeah, in fact, that's exactly why you put a lot of redundancy into the system, especially for equipments like pumps and blowers or compressors. Compressors, no, sorry, but yeah, for the pumps maybe. So this is your basic block diagram for a system in combination. Now let's see what the calculation is. We saw that earlier in series, the calculation, the overall availability was 0.87, then it went to 0.99. And now let's see what happens when you have equipments in combination of series and parallel. Yeah, so what you do during this stage is you basically bring down the systems to one single component. So you see block 2 was basically initially it was 3 equipments in parallel, and then you brought it down. You did the first calculation for block 2, and then you brought it down and you aligned it with your block 1 or unit 1 or unit 2, and then you consider the whole system instead of a combination. You start considering it as a single string of equipments in series. And now you calculate the reliability. The reliability has gone up to 0.9023%. So that's your reliability for the system altogether. It's higher than your equipments in series, but it's lower than your putting all your equipments in parallel. It's somewhere in between equipment in series and equipments in parallel, but it's not really practical to have 3 trains or 3 entire strings in parallel for all your equipments. So it's all about managing your assets again. So cost benefit analysis for everything. Yeah, we go to the next slide. Yeah, so now this is again the calculation. If you want to look at it, you can see how I've done the calculation. So you have each block represented separately. You first calculate the blocks where you have a lot of equipments, most of them in parallel together. Then you calculate the ones in strings together, and then you combine it as a system. Now, this is the same philosophy that we will use for the RAM analysis through the entire life cycle of the plant. or not the life cycle, but for the entire calculation of the RAM analysis, right? So I don't know if so it mentions first calculate the reliability for each block individually, and once each block is calculate the reliability of the system in totality. Okay, so this is your calculation that you will use, or your spreadsheet that you will use as a basis to do your entire calculation. And in the end, you will get one final value to represent your availability, which is yeah, whatever percent that you get at the end of the calculation. Right. Next, maintainability.
Mr. Kevin, one more clarity.
Yeah.
One more clarity required. Here, on parallel connection, we are getting better score. What is the reason behind that? On series, we are not getting good score. Here, 99, 98% we are getting in parallel.
Yeah, it's quite simple. Like say now if you have two equipments and if one fails, if you look at it in reality, say you have three valves that are connected in series, right? Three valves that are connected in series. Your first valve fails. Yeah, you could have actually a plant shutdown even if your other two valves are available, right? If you have three valves in line, so your two block valves, imagine your first valve actually fails, and imagine if it's in series, basically you have no feed that's being processed. So yeah, that means there's no protection. You actually get a trip if one of these valves fails. It basically reduces everything, your whole reliability. But if you have something in parallel, even if one of the pump fails, you have feed that can go into the other pump, and you can still get an output. So this is the basis where you can understand why you put things in series and parallel. This is the whole concept, that you can get more reliability into the system. You can just imagine if you have one feed and you have two lines one going to your pump.
Yeah, got it.
Yeah,
got it. Thank you.
You're welcome. So we were talking about maintainability. Maintainability is the ability of the system under a given condition of use to be retained or restored in a state in which it is performed, in which it can perform a required function when maintenance is performed under given condition. Yeah, so it's basically the idea that you want to retain or you restore your equipment as soon as possible. So if you're in operations and your plant or your equipment fails or your pump fails, yeah, your operations crew calls the maintenance person and says, yeah, the mechanical seal has failed or your bearings are all in a failed state. Maintenance might come and do your task in 1 hour. They can do it in 2 hours. Maybe the same task they'll do in 6 hours, depending on maybe whether your spares are available. Maybe your maintenance person is not available. So you can have all kinds of delays in reality. Maybe you need to overhaul your equipment. You don't have a crane to overhaul your equipment. So there can be lots of delays in the system. So you can always work on improving the systems when you calculate your mean time to repair. And that is what maintainability is about, is how fast you can bring your equipment. It doesn't have to always be about an equipment failure. It can even be during your plant shutdown. Many times people do studies on extension of plant shutdowns, and it's always you look at ways to improve your entire system. So that is maintainability. It's represented as normally represented as MTTR, mean time to repair. So you have MTTF, which we discussed earlier, mean time to failure, and MTBF, which talks about the same thing, but yeah, the difference between MTTF and MTBF is basically MTTF talks about non-repairable system. So if you have bulbs in your house, you don't really repair it; you just throw it away. So you put in another bulb, and then yeah, once that fails, yeah, same thing with gaskets or any small component in your plant where you really don't go for repairing your system, you just replace the component. It makes a lot more sense. So then in those cases, you say mean time to repair. If you talk about equipments that you repair, like your pumps, your compressors, or your vessels, you might do a little bit of fabrication. You might do thickness monitoring. You might see the sheets are corroded, or the thickness has reduced, then you go for replacing. You do a bit of repair or patchwork on your vessels. So that's all about MTBF. I know my charge is a bit low. In RAMS, I really can't see. Sorry, I'm on my phone. In RAMS, the primary concern is how to increase availability by reducing scheduled maintenance and unplanned maintenance. So these are the two primary objectives in maintainability, is basically to reduce your planned and unplanned shutdowns, the time. Right, we go to the next slide. This is your typical process of how your equipment fails. So you can see a straight line. It goes down to a slanted line. So the straight line basically indicates your equipment is running smoothly. And then the moment it starts dropping down, that's the point it's failed. It goes down to a failed state. It goes straight ahead. Then once you do a little bit of you prepare for your equipment, you prepare for your maintenance crew to come, you wait for your permits to be approved. You do all those activities. So you see there's a preparation and delay, and then there's a time you actually do so a bit of maintenance, and then there's a waiting time, and then there's a ramp up time. And then it's up, you start up your equipment, and then it's running again. Now it's important you note that the rundown time and the ramp up time, these two are basically not considered as downtime. So your equipment might have failed earlier, but you're not actually going to straight away to a complete loss in production. There's a slow process in which your equipment or your entire facility is ramped down. So if you are running a 500 MMSCF facility, it might take a day or maybe 12 hours, 6 hours to bring it down. So you actually have protection during that time. It's maybe not 100% production, but it's still production, and it's not counted as your equipment failure time. So if you look at the downtime, you can see there's a bit 2 arrows that stretch between your rundown time and doesn't include the slanted lines, your rundown time and your ramp up time. So it's important when you actually look at the RAM analysis, when you put in your data, to make sure understand that once the equipment is running, it's basically considered as available. The point where it's not actually running 100% actually comes at your operability factor, and that's another factor in addition to reliability, availability, and maintainability. It's another factor which is not considered. It's considered doing some analysis. Some people do. If you're working with the DNV, if DNV uses software like Maros, which also talks about your process optimization. This is what you call about process optimization. It says your plant can actually run this much, but even if your actual availability is saying is very high, you can do a lot better if you reduce your rundown time and your ramp up time. So anyway, this is basically just a typical flow process for your MTTF and MTTR. Okay, so we go to the next slide. This is basically the calculation for availability. Availability is the ability to maintain ability of the item to be in a state to perform a required function under given conditions, given instant of time over a specific interval. Reliability and availability sometimes can be confused. It's important you realize in availability, the only difference between availability and reliability is basically really when you consider your plant maintenance also into your availability. There's a factor of plant maintenance. So if you're saying your plant is up for reliability, you can say you can only the MTTR or your downtime. When you calculate your downtime in reliability, you only put your mean time to repair. But when you calculate it for availability, for the MTTR, you will also consider your plant maintenance. So that means if this year you are doing plant maintenance, and next year, if this year you're doing plant maintenance, basically your reliability will be high, but your availability will still be low, because even if your equipments are reliable, it's not available because your plant is under a planned shutdown period. So normally your shutdowns extend for a month. So every year your plant does plant maintenance. It's likely that your target KPIs or your balance scorecards for that year would indicate that the availability is lower than your reliability, because if you look into the formula, availability equals uptime by uptime plus downtime, or MTTF by MTTR. The mean time to repair will include your scheduled maintenance for availability, and it will not include it for your reliability. So this is the only difference. If you're wondering what is the difference between reliability and availability. So this is your calculation again. Uptime is the total time your plant is running divided by the time it is running plus the time it is completely down. So we can go to the next slide. It'll give you a more clearer picture. Yeah. So this is a availability of a typical system. Imagine your plant is running or your equipment is running. It runs for 3 hours. Yeah, the plant goes down after 3 hours. It's down for 2 hours. Then it comes up again. Then it runs for another 2 hours. It goes down 2 hours. Then it runs for 1 hour. I really can't see it from my phone. Then it runs for another 4 hours. So the total time that your plant is actually running are the number of hours that are marked in green. So it's 3 plus 2 plus 4. 9 hours is the total time your plant is up. So now you go to the total time your plant is down due to an equipment failure or due to a scheduled maintenance, whatever it is. The downtime is 2 hours initially, and then it's 1 hour. Yeah, so it's your downtime is basically 3 hours. So you do the calculation based on availability equal to uptime by uptime plus downtime. You get this is the figure, and this is how you get it. And then you have your percentage of availability. You go to the next slide. Now this is the actual manner in which you actually do your distributions to calculate your availability. Is not about your equipments. It's not only about your equipments in series and parallel. You also talk about an R out of N series. So when you run a plant, someone was asking me earlier, how do you get reliability increased? Yeah, so this is a typical example. You have 50%, 50%, and 50% of your metering skid we had seen earlier, and you see 2 of the pumps are running. Yeah, if one of the pump fails, so you can have different conditions, or different possibilities of outcomes during the life cycle of your plant. You can have one possibility where all your pumps are running. There's always a possibility that you can have one of the pumps down. You can have a possibility where you can have 2 pumps down. You can still have 1 pump running, and there's a possibility that you can have all 3 of them down. So yeah, when you do a calculation on your availability, you basically do it as a combination of all these possibilities, and that's why you say a load sharing concept is R out of N. So yeah, so if you do a combination of this basically. Sometimes you very specifically say you need to have at least one of the system working or not. It all depends on the requirement, but this is your calculation which you normally use for your actual reliability calculation for equipments that are in parallel. Right? We can go to the next slide. So yeah, so that you normally use the formula. What you see is the formula that you normally use for calculating your R out of N series. It's normally expressed as permutations and combinations. Not permutations. You don't use permutation. You just need combinations. So if you know your NCR calculations, yeah. So where N is you're basically the number of pumps in totality. You have 4 pumps, and you have X, which is basically how much pumps of this is are you expecting to be running? So it could be one pump, it could be two pumps. What we actually do is we consider all the possible scenarios. So we consider zero pump, one pump working, we consider possible two pumps working, and you combine all the reliability probability calculations to combine it together. Right? So this is just something I thought you need to keep in mind. This is the normal formula that you actually use for your binomial district or your load sharing facilities. I even said about derating. It's also one of the things. You might, if your one pump fails, you might have to increase the capacity of the other pump. You can all include it in your calculations to finally get your actual availability. Right? We can go to the next slide. So safety, and now we go to safety. Safety, like I said, will always be an integral part of your study. Doesn't matter where it is. If your equipment fails, you need to make sure it fails safe. So you have all these studies to make sure all these processes in place, which already takes care of that. You do still studies to make sure the protective systems that are in place for to protect your equipments are very reliable. You do all those still assessments, still verifications, all the safety integrated functions, safety instrumented functions. They're all made verified, made sure that your equipment really doesn't cause you any major incident or failure or death or anything associated to safety. But it's important that people know that there are legal obligations for your companies, because that is always the most important thing that drives management to focus on safety. It's helped me a lot personally. I've specifically mentioned the international law because many countries, if you go to the Middle East, especially, they don't really value a person who comes from outside. They don't care if something happens to you. Yeah, you always have the systems, it's all good. But the reality is sometimes it doesn't really show on the management point of view. It's all good on paper. People love to put it on paper, but in reality, sometimes you can. I personally had an issue, so I can really reiterate this this standard. I really can't see it. I believe it's the C-155, yeah, the convention C-155 of the International Labour Organization. So International Labour Organization is what I call the mother of all safety organizations, because it's an international organization associated with the United Nations. It basically gives out basic standard conditions that all companies, all employers, everybody should maintain to make sure that your company is safe. So it's oh yeah, I can zoom it. So it says, as per Article 16, Part 4, action on the level of the undertaking of the owner. It's a bit mistyped in. It's the undertaking of the owner. ILO Occupational Safety and Health Convention, 1981. So this was basically ratified by, or this was firstly prepared in 1981 and was ratified by all the countries. So India is part of the ILO, so we are basically obliged to follow the ILO conventions. I remember I was working with a company once. I had a lot of safety health issues. I left the company. 3 years later, I did a course on NEBOSH, and the instructor in NEBOSH, he for some reason, he was mentioning this topic on the international law and how important it is, and kind of struck a chord. And I wasn't really focused on studies anymore, because I was now more concerned about the legal aspects of it. So what I did is, yeah, I was working in this one company in the Middle East, I remember. Right? So 3 years later, that's when I did the NEBOSH course. 3 years later, I prepared a detailed root cause analysis report on my health conditions, what are the factors that affected it, and it all came down to international law and labor law. and all those aspects of legal aspects. I sent it out to the CEO, the DCOs, the top management. I even sent it to the chairman of the Petroleum Corporation. Yeah. So the reason I did it, because I knew I was on the right side, and it was something I told them many times, but they never accepted it. It's part of the safety culture. People expect you to work like machines. Sometimes, yeah, it's there in every company, I'm sure. It's there. It might be there in your companies too, or not. Management really expects you to put 150% of yourself. Sometimes it affects your health. So anyway, I sent this report to the CEO of the company. Just 3 years later, because they put me, they sent me off because I was causing. They didn't really do an investigation of what was the cause of my failure. They didn't give me any settlement, nothing. I didn't get my payments. So all these things. The most important thing was I suffered a health injury that was permanent in nature. So when this specific law came and I was introduced to this law, yeah, I've been 17 years in safety, but I never knew the importance of this law, and this is why I want to share it with you. All I had to do was send one report to all these personalities. I sent a 300-page report telling about all these things, all the legal violations of the company. I sent it out to the CEO. Guess what happened? Nothing. Yeah, no response from the company. So yeah, that's exactly what I expected. You don't expect management to just walk up to you and say, yeah, we did something wrong, and we will compensate you. But the good thing is you still have legal bodies. This is a government company, so you can't go to the legal department or the labor department because they will always favor the national bodies, especially if you're in the Middle East. So what I did is I escalated the incident to the International Labor Organization. Yeah, what happens is next day I get a call from the management saying, yeah, I will give you, please send us your account number. So this is the power of labor, of your national or international laws. Is people are afraid. It's not that they're afraid of you, but things can get really messy if they're taken to the court of law, especially international borders. It can affect your reputation. It can affect everything. Imagine if something happens in your company and it goes all over Facebook or WhatsApp. Yeah, it really affects your reputation because now you have a lot of social media, and it really affects your client base, database, your customers, everything. So it's important that you realize that companies have a legal obligation, and you have the power to enforce it, every single person. So what does this specific law say? I want to reiterate, I specifically use the same standard to take action against the CEO of a company, and actually worked out. And it's something that everybody should keep in mind. This is what safety is. Safety is very, very powerful. And it's something that you have to always think about, that you cannot compromise it, even if the management tells you, even if the boss tells you, even if anybody tells you, you can always stick your ground and say safety will not be compromised. So this is what the law says. Employees shall ensure, or the employer shall be required to ensure that as far as reasonably practical, yeah, the workplace, machinery, equipment, and process under the control are safe and without risk to health. So that's so if you specifically look, your machinery and process under their control are safe and without risk to health. So yeah, so this is why you cannot exclude safety from your equipment. So even if reliability basically talks about maintaining your equipments, making sure your equipments are available all the time so that there's no production loss, you will always not compromise if your equipment is a safety critical element. That's why all your fire protection devices, like your fire detectors, your fire monitors, your fire hydrants, fire pumps, they're all given the highest criticality in your company, even if it's not actually affecting production. It might still be given the highest priority. Your maintenance frequencies will always be high. Yeah, it would bring down your availability because you're doing a lot of maintenance. You might do a lot of functional testing. You do testing on your detectors. You might do testing on your monitors. You might do a lot of functional testing on your equipment. but it doesn't matter as long as it's all safety. Yeah, it does matter if it's a business critical equipment, but as long as it's safety, you cannot compromise. So RAMS and safety, you cannot really try to bring down availability when it comes to safety, but you should also not consider increasing safety too much. Yeah, then it can be a problem too, especially when it comes to instrumentations. If you increase the safety a lot, the safety factor, you can have a lot of nuisance strips, and that's one of the things process safety they sitting in the engineering offices in operations. They basically sit and try to see which of shit.
Looks like Kevin is logged out.
What happened?
I think Kevin has been logged out. I think you have to log in again.
Oof. Oof. I think 5 or 6 slides are left. Not more than that.
You wait, maybe I think not reachable on mobile.
The number you're calling is currently switched. The number you're calling.
Yep.
Yeah, Kevin, you are back. Kevin. Kevin, you are not audible. Yeah, Kevin, you can go ahead.
Yes.
Hello? Hello? Can anybody?
I think Kevin, it's okay.
Even you can mute one of the device, either laptop or mobile. Both together are making echo sound.
I don't know if
Okay.
you can hear me.
It's fine, Kevin. Yeah.
Oh, you can hear me?
Yes.
Yes.
Okay. Yeah. So I think the headphones did the job. So this is what we were talking about. So I'm sorry about the delay. Okay, so I mentioned earlier about the international law. Now this is the national law. We talk about the Factories Act as per Section 7A, general duties of the occupier. Every employer shall ensure, as far as it is reasonably practical, the provision and maintenance of systems in the factory are safe, as low as reasonably practical. So this is where risk matrices come into the picture and make sure that your risk is as low as reasonably practical. Yeah, so these are the two laws you need to be always kept in mind, because it's very important that everybody knows their rights, because this is the only thing that you can go back to if your company is violating your safety. So we go to the next slide. Safety and reliability. You can see all those studies. It was mentioned earlier. You have the SIL study, your EIA, environmental impact assessment, quantitative risk assessment, HSE studies. So what it says over here is, though each of these safety studies have different objectives and are performed independently with specifically designated teams, at different stages as per requirement or as per standard, the inputs or outputs of these studies may be used or referred while performing RAM analysis. So your safety critical elements can distinguish what are the equipments that you need to consider for your study. Your SIL verification can also be used. So SIL gives you what is the reliability. If you know what is your SIL rating for your equipment, you pretty much know what is the probability of failure, or what is the reliability. You can calculate your availability based on that. It's not that easy. You normally have very specialized people for you people with SIL certifications. HSE study, you talk about possible deviations, the no MLA PRO concept. You come out with recommendations, and your recommendations are basically used as inputs of new equipments that will be probably designed from your HSE recommendation, and you can basically include it into your RAM analysis. So that's why you have RAM analysis at each and every stage, because you do HSE studies, restudies every 5 years or something, depending on the requirement or your standards. But what I understand is your PHA studies or HSE studies are normally done every 5 years. You revisit your HSE and look at all the possible deviations that were not considered. Sometimes you use your root cause analysis that you do as a part of your reliability studies, and you include it into your HSE studies. Your HSE studies can be reused into your RAM analysis. So there's a lot of integration between reliability and safety. But the problem is most companies don't really use this benefit to the best of their capacity. Most of the time, safety and reliability are very separated, and you really don't get them working together, especially process safety and reliability. So here you have a standard IS 14224, which lists the different interrelation between various data that can be used in commonality in the various safety studies. So if you go to your IS 14,000, it lists all the data that is required, which can be used or exchanged between all these studies. There's a table, I think table D2 or D6 of IS 14,000. Basically tells you, it's even though the document is titled exchange of liability data, it basically specifies which of this data can be used for sales studies, and the same data can also be used for your RAM analysis, or also for your safety critical elements, or your QRA, or your EIA. So there's an integration. That's what you need to keep in mind, and always think about integrating. So we go to the next slide. Safety critical elements. I think I discussed this, but this is something that most companies do. Shell has a specific design engineering practice for your SEs. I don't know if you can hear me. I'm getting a lot of disturbance. Is that, are you facing that too?
I think you can switch off one of your devices, Kevin. I think both devices are on.
No, my phone is actually not functioning.
I think the phone would still picking up, because there are two Kevin shown on the participant list, and both mics are on.
Strange. My phone is actually blacked out.
Okay,
I don't see how it is functioning, but let me see if I can just change the location of my phone. Is this better?
Yeah,
That's
go
better,
ahead.
is it? Just give me a
Go
second.
ahead.
Hello?
Yeah, go ahead.
Yeah. Sorry, it's, I don't know, Samsung phone. So we go. Safety critical element. What is safety critical element? It's an item, equipment, or structure whose failure could lead to a major accident. Safety critical element is actually same as any other component. You can have a pump, which is a safety critical element. You can have a compressor, which is safety. There are different categories or categorized sections in which how your equipments can be classified as a safety critical element. So safety critical element is primarily a safety study. It is probably the most beneficial to the reliability department, or your defining the equipment for your RAM analysis. So again, it's an item, failure could lead to a major accident, your equipment. Right? So major accident, we're talking about high risk, severity, that has a potential to lead to multiple failures. We talk about performance standards. Once your safety critical element is developed, then you start developing performance standards to ensure that pump have all function as it's supposed to, based on each SE will have a performance. Performance standard is basically like maintenance task. It will also consider or ensure that equipment is functioning from a design requirement, not just from a meeting. Okay, next slide. So yeah, here are the different categories of safety. So you have equipment taking hazardous pressure vessels, pumps, compressors, containment is you have containment control equipment like your relief valve, your vent valve, your check slow down valves. They're all aid in containment operation. Shutdown control or pressure elements. Safety definition. Cell valve, emergency valves. We talk control it, release equipment. There's some call. I don't know if anybody
So anyway, you have active mitigation system, your fire protection system. They are all so you have all these classifications for safety critical elements and standards, and technically every single component in your plant, if you go by this, it's classified as safety critical elements. So yeah, good thing that at least you do a basic RAM analysis. Covers all the equipment. So this safety critical elements, I don't know how much time we have. I think I've already taken a lot of time. Try to process this. Okay, so you go to the next slide. So this is what your performance standard is like. That's what is your requirement. That's what is at the top. Goal is basically boundary and functional requirement to the system. What is the system? We talk fire pump. What is the safety and the functional requirement? Right to do start on the what is the criteria? Yes, what is the criteria? So start with initiation. Reference document basically specific standard that says specific is an SE classification for equipment. All pumps will not be categorized as an SE utility. What is the insurance task? Now you need to understand this is done by facilitated and safety talking about performance assurance. What is the task? The maintenance task that's required to pump is functioning properly. Now it's not only about fire pumps, it's basically all pumps. They're all tried as only about dangerous. Pumps are not considered as equipment that have to contain, but you make your West people, but basically also maintenance. This helps you actually with your RC and stuff, preventive maintenance strategy, active maintenance. My sound is not. How is it now? Better? Hello? Is it better? Vipin,
Yeah, go ahead, Kevin.
this is performance.
It's breaking. Your voice is little breaking.
How about now?
Yeah, better, far better.
So we can go to the next slide. So this is just basically an indication. Okay, yeah, here you have it.
Yeah,
you have a safety
yeah, go ahead.
critical
Now
element,
clear. Yeah.
which is basically part of the can be used as input for your RAM analysis. Identify the equipments that needs to be modeled for your RAM analysis. So sometimes you decide you don't want to use an equipment, you remove it from your model, and then you do your RAM analysis. So during initial stages, the management might decide we will not include your less critical equipment, like maybe your utilities or maybe your freshwater pumps or anything that's not really affecting production and also not affecting safety. So once you decide your safety critical equipment, you can include it into your RAM analysis. So this is all how normally you can include your safety studies into your reliability studies. Still not clear. Is it? Yeah, I'll try to wind it up pretty fast. I don't think I'm going to extend this along. Back. I've already. You can go to the next slide. Will all be less the same. Yeah. So you have safety critical elements. It's how a safety study is linked to your reliability or RAMS analysis study. So each stage used at a stage with RAMS analysis help you identify your RAMS analysis, find your strategies, right, with your targets. So managing deviations, and when you're trying to analyze and improve, you're trying to set targets in RAM analysis. So we go to the next one. I'm sorry about sound quality. So here you have QRA and RAMS. So QRA has a is a risk management process. So you have QRA studies approach. So you have first hazard identification, then you have consequence modeling, frequency estimations. So you calculate your risk, then your risk reduction measures. Those are your recommendations that come from your QRA and how you implement it. So based on your QRAs, you might. The only problem is recommendations might be a bit different for your QRAs and RAM analysis. More or less, use the same inputs. So hazard in QRA helps to identify RAM failures have potential to release hazardous material. So calculate the consequence. So you do a QRA on a specific hazard on a specific equipment. You can basically use it also to calculate consequence in your risk matrix in your RAMS. So you don't do an additional set of jobs. So that's your hazard identification. Next process where you do your consequence modeling frequency. Yeah. You shift the. Okay. So that's more or less the whole process. So we go to SIL studies. There are lots of specialized people in SIL studies. We don't need to go too much in details. The only thing you need to realize over here, there are probability, there's a safety availability requirement that's already set. Once you know your equipment SIL levels, you know what is the required availability that is required. So it's pretty much already predefined. You don't need to do another calculation. Just directly use your equipments once you know their SIL levels because the availability is already calculated. Right, go to, so you have these different standards. Those standards are basically ISIL standards. You have performance levels. This is also correlated to your SIL, but it's more related to your machinery. You have ISO 13849, safety of machinery. It tells you about the performance levels and how it needs to be maintained. And you have all these different probability distributions that you take into your mind before you calculate the performance level. So you can see, oh yeah, PL rating can be converted to SIL rating, so, and vice versa. You can go to the next slide. So this is basically your left side. You can see a typical SIL certification. So it basically says what is the SIL rating for your equipment. So basically, vendors give you a SIL certificate of the equipment, so you can get a confirmation. You go factory acceptance test, then you confirm it. Then you use the same equipment reliability available into the structure. This is downstairs. You can see the typical layout of a safety instrument function. Consists of sensors, logics, final control elements, like your control valves, which helps you control your process. Next slide. So typical challenges for performing RAMS. Reliability data. The data, media data, is more important substance you want for your calculation. Normally, you have databases readily available. It's either available with companies like DNV, Vectra, your consultants. They have their very own set of documents which they've been collecting over years. Many companies always prefer that you do a RAM analysis specifically with your consultants like DNB, especially DNB, they have softwares just for RAM analysis that have been developed right from the beginning. Then you can use their data if you want. What most people normally use is your offshore reliability data handbook, which is prepared by Intef and NT. Yeah, so Vipin has something to say. Vipin, you want to say something about SIL? Maybe still Vipin is an expert in what I feel in SIL studies. We go to Vipin, maybe you want to say something about your SIL and how it's related to RAMS?
See, basically for process safety related items, we basically go for the SIL analysis, whether to make sure they functions best during their related required levels. Like we do analyze the probability of failure on demand, the risk reduction factor, and then we basically go for the required SIL rating. And then we basically purchase the equipment so that they functions basically on a needed level. So that is basically the thing which we do. So like, for example, the ESDs which we purchase basically should have a redundancy of 1 out of 3, 1003 configuration. That is what basically which we do while we use while basically taking into consideration such equipments do perform at their basic levels.
Perfect.
So that is the thing. And the second thing, basically, likewise, for example, since the IEC 16511 or 16508 talks about safety integrity levels for that, basically for process related equipment and machinery or for process safety performance. Likewise, for engineering industry, for equipments, machinery, and other where more human interventions are possible. There is a standard for calculating the probability of failure on demand, or PFH, or more likely to be the probability of a failure per hour of the equipment. And it's rated safety related parts, like for example, a two-hand trip or a presence sensing device or a movable barrier device, whether it fails or not, or whether it go for its intended functions during the time when it acts. So that is basically done using the ISO 13849 part 1 and 2, ISO 13849 part 1 and 2, and a specific machine safety guide. So that basically is equivalent to what we do as a SIL rating for the equipments also. Yeah.
Right. Thanks, Vipin. And a patient explanation of the concept of reliability, availability, maintainability, and safety. I think a very extensive coverage in short duration of 2 hours. Sincere thanks from all of us. And we move to the question answers. Questions from the participants, they can unmute and ask the questions. And also, parallelly, I would request the participants to go to the chat and then give a feedback by clicking on provided in the chat box.
Yeah, the one question related to the performance level. We have seen a slide with the performance level up to 3, SIL performance level 3. SIL 4, do we not consider in that performance level chart?
See, basically, sir, to intervene, SIL 4 basically, yeah, it is basically considered, but basically it is mainly I found that it is basically used for nuclear reactors and other things where much more protection is needed. So SIL 4 rating is, yes, it is basically considered, but on a higher scale where risk levels are more and the quantity of people or the things affected is more, we go for SIL. That's it. Especially that
mainly the societal risk.
laptop close.
Yeah. No, but basically yes, that is one thing. Second, if you consider nuclear facilities, almost all the equipments might be silver rated.
Okay, I never come across, but that's a correct thing, because there are more and more safety requirements.
The probability of failure will be less,
So,
but once when it fails, it will be a big catastrophe. Like you have seen the recent Fukushima thing also, no? The failure will be more catastrophic. That is why mostly they go for silver rating. I have read about some papers where silver rating is basically used in nuclear reactors. Yeah.
Correct. I never come across, because I am limited with the process industry. So maximum SIL 3 only we have. SIL 4 never
3
had.
now,
Of course,
nowadays SIL 3
industry
is
could be there.
basically for refineries. But for ours where we use hydrogen as this thing, we basically have SIL 2 only, not even up to SIL 3. Refineries basically and LNG facilities basically now go for SIL 3. Yeah.
Correct. And what about the QRA latest, the software version? Before I had 8.3, PH, Pastrix 8.3. Now, is there any updated version for that with DNB or through other software developers? Any latest version?
No, we use other thing. We use ZHA thing and not DNVs. So I don't have much of an idea. Earlier I used, but not now. See, now the questions are not asked to Kevin. It's asked to Kevin only. Sorry. So over to you, Kevin.
Someone answering that.
Yeah.
Yeah, Vipin, it's good because I am dealing more with reliability. So you seem to know more on QRA and SIL studies. So it's good that you could answer the question. So you did a better job. So good, thank you.
Thank you, Mr. Kevin, and thank you, Mr. Vipin. Thanks a lot. Very well explained.
Right.
Any other person? Please unmute and ask. Otherwise, we will move to wait for a few seconds. Okay, I think if there are no questions, I think we move to formal vote of thanks. Request joint convener Meenu of thanks.
Thank you, sir. I deem it as a great honor and privilege to propose the vote of thanks on this occasion. Let me first of all thank our chief speaker of the day, Sri Kevin Cherian, sir. Is professionally a reliability consultant who enlightened us with the technical aspects of reliability, maintenance, availability, and sustainability and its applications. Thank you, sir. Then I would like to thank Dr. V.M. Ramesh, sir, Honorary Secretary of National Safety Council Kerala chapter, to deliver the welcome address. And then I would like to thank Sri Nitish Devaraj, Senior Inspector of Factories and Boilers, Government of India, Government of Kerala, to deliver the inaugural address and to grace this occasion. And despite their busy schedule, then I would like to thank Sri Nayan Nandakumar, sir, Senior Associate Vice President of Carborundum Universal Limited, as well as the convener of HSE Forum, to conduct and coordinate this webinar in a nice manner. Thank you, sir. Then, but last not but not least, I thank all who are present here for paying the attention and have a great day. Thank you all for joining us. Thank you.
Thank you very much. We meet next month for an interesting session like this. So thanks to all, and hope everybody has given a feedback on the talk today, which helps us to make it a better when we provide the evening talk next month. Thank you very much. Thank you all.
Okay, sir. Thanks a lot.
Thank you, sir. Thank you, sir.
Okay.